Stream. Ça y est, ça marche.
On est sur le web. Bon, il faut que je fasse sérieux alors.
On dirait qu'il y a, je sais pas, il y a pas beaucoup de lag, il y a quelques secondes, je pense, il y a 3 secondes de lag à peu près.
Toi?
J'ai l'impression qu'il y a 3 secondes de lag avec YouTube. Pas énorme. On met l'annonce du coup pour le stream YouTube?
Yeah.
Tu la mets ou jamais?
Je te laisse.
Donc je dis qu'il pose des questions par chat, on est d'accord?
Yeah. Il ne faudra pas le louper.
Tu perds la qui, Alain?
Non, j'ai dit il ne faudra pas le louper à la connexion. L'utilisateur a le droit de présenter. Hi, Caroline.
Bonjour.
Hi, Corinne. I think Dave is already connected.
Yeah, I'm here.
Hi, Dave.
Hello.
Hi. I just want to see I haven't used this interface before, about presenting.
Okay, so you can turn on your camera at the,
I see.
bottom,
Okay.
the right mouse button at the bottom. Yes.
I guess I might as well do high quality. I guess, why not? That works. Okay. And then if I say start sharing. Okay, and then share my screen. All right.
Yes, you can either share your screen or upload the presentation. You have this plus button at the leftmost one.
Okay, I'm using Google Slides. Is it better to upload it? Is that more dependable or something?
But I think if you share your screen, you will not see people who are connected. Yeah.
Okay, let me go ahead. I could try downloading the talk. And so if I download it as PowerPoint, you can display it?
Yes, I think PowerPoint or PDF works.
Yeah, my slides are let's do download Microsoft PowerPoint. Here we go. Figured this might happen. All right, so let me cancel that. Cancel. Okay. Okay. Yep. Okay, let me just look. What's the weather like? Where are you in France, by the way?
I'm in Lyon, so I'm Alain Chana.
Yeah.
Caroline is in Rennes. Caroline, your mic is off, yes.
Yeah, you have nice weather here.
Yeah, I bet.
And Renaud is in Grenoble.
Oh, boy. They all sound very nice.
So Lyon and Grenoble are in the southeast part, and Rennes is in Brittany, the western part.
Okay, let me try and present this version, see if it still looks okay. Yeah. Okay, I'm just checking the slides to make sure it works, but it looks good so far. You know about how many people are going to be online?
I hope more than, 100. Or we also have a YouTube link, so we are broadcasting the talk.
Google's getting better at this downloading. Okay. Oh, that's right. I've got two. If that happens, I'll if we have time, I'll just do the story from my Google Slides. But okay. No, oops. I lost the window. Okay. So now just plus that.
Yeah.
Upload a presentation. All right. Drag here. Upload. Well, wait a minute. Oh, it's converting the file right now. I see. Okay.
Good.
All right. It change the fonts a little bit, but that'll probably, hopefully I can give the time. All right, and then I just make the slides go forward like, no, okay. It's just a delay. Got it. All right. Whew. Got 3 minutes to spare.
Cool.
So I think this talks about 45-ish minutes, maybe 50. And then I could have time for questions. And then, so is it a 1 hour slot or an hour and a half slot?
As you want. Let us say up to 2 hours.
Okay.
As long as it gets. I mean, we're so happy to have you. I mean.
Yeah.
Okay. Well, then what I'd like to do is kind of give the technical talk and answer questions about it. And then one of my colleagues started doing this at the end, kind of give my life story, because people think that if you've been successful, unlike them, you've had no problems in your career. Everything's just been smooth. Everything's been perfect. No bumps in the road. And so I'll tell my life story and lessons learned to pass along to the next generation. But now that's about 15-ish minutes. And it's usually pretty entertaining, but it's about 15 minutes there at the end. So.
Okay, so we have a short introduction. So maybe can we start, Renaud? Or?
Maybe we should wait 2 more minutes because, French people usually, they're not really coming ahead of time. So I think we still have people connecting.
Yeah.
And we are reaching 100 people, yes. If we take into account also the YouTube people, we're over 100 now.
All right. Triple digits. Okay. All right.
So it's 6 a.m. in California, Dave.
Yes, it's early. I do get up early kind of naturally, but I was really great. You sent email reminding me of that so I could set my alarm.
I think maybe this is one of the part of your secret. You wake up very early.
Yeah. Well, I think part of the secrets is to figure out when you're most productive, right? Whenever that is. When I was younger, it was in the evenings. But once I had kids, I had to convert to a morning person. And so I became a morning person, and that's more or less stuck. But, kind of the worst thing to do is answer email in your most productive time and then not find time to really concentrate. And so you got to figure that out for yourself. But for me, I don't need as much sleep. I kind of got that from my mom. I'm probably okay with about 6 hours of sleep a night, so I can get up early and get a lot of work done. Okay. Got a reminder on my watch what time it is.
Should we start?
Okay. We still have lots of people connecting, so maybe you can wait 1 more extra minute if that's okay, and then we start.
Sure. So is school over now in France? No, still going?
No.
Okay.
Yeah, still going to the end of June.
End of June, okay.
But mostly, some people are doing internships and things like that, but they still have a defense to pass or backup exams.
Mm.
Okay.
I think we can go, Alain.
Yes. Okay. So, thank you again, Dave, for accepting this invitation. And I will manage this session with Caroline and Renaud in Grenoble. So Caroline is Rennes. And yes, I will give the floor to Caroline in order to introduce you.
Okay, so good afternoon, everyone. So we'll have David Patterson today talking about the energy and carbon emission of neural architecture search and large model training. It's a pleasure for us to have Dave today. He was accepted to give a talk to the French research community early in the morning. So Dave is a professor at UC Berkeley and also a Google Distinguished Engineer. Dave is one of the most influential computer science researchers in the world. So he has received several awards during his career. So it will take the whole day to enumerate all of them. So I will only mention that he shared the 2017 ACM Turing Award with John Hennessy. And he's also the main initiator of RISC-V. And he published the best-selling textbook in the computer architecture. So without further ado, so Dave, the floor is yours.
Okay.
So we ask question at the end of the presentation, right?
Say that again.
For questions, do you want them at the end of the presentation?
Yeah, let's try it that way. I think it's about, like I said, I think it's about 45 minutes of talks, and then what we'll do is we'll have a question and answer period as long as that lasts, and then as I like to do what I've been doing for the last about 5 years or so is tell my kind of life story and lessons learned over my 50 years in the field and to pass along kind of the younger generation so you can avoid the mistakes that I made, learn from my mistakes. And that's usually, that has entertainment value, even though it's a long thing. So let's go ahead and get started. Okay, so there's been, I kind of got into this, I think, partially because of this publication on the right. So I was president of the Association for Computing Machinery. So our flagship magazine is the Communications ACM, especially early in the computing era. This was the prestige magazine, and I think it's returned to some of its luster. And the cover story last December was Green AI. So I got interested in this. This is not something I'm an expert in. I've always, tried to do the right thing for the environment, but that I hadn't been, the top thing that driven what I've done. And so I started on this journey to learn more about it, particularly machine learning and climate change. Now, as I looked into it, Google's actually done a lot of stuff around this. That Google has tried to have energy efficient data centers and has kind of bragged about it and published information about it. I have been involved with what they've been doing in hardware design processors for machine learning. Google has announced 5 generations of those. So in that area. And then Google's made announcements as a corporation about goals for climate change. But I wasn't very aware of that. But it's been going on for almost 15 years here at Google. Now, recently, there's been a lot of attention, both in the public and in the press and in the research community. What about machine learning? Machine learning models are getting bigger. What's the environmental impact of that? I'd list some of the papers there. A paper by Emma Struble was one of the early papers there. And in fact, this Green AI paper cites it. It's the first thing they cite, and they cite it as the most frequent citation. And since then, there have been people who've tried to help people calculate it by creating calculators. I'll talk about some of those calculators in the talk. And recently, our colleagues at Stanford, about the same time we were doing this, a little earlier than us, one of the PhD students, Henderson, was also kind of investigating this area. We didn't actually know that he was doing that. It was kind of embarrassing to figure that out, that somebody at Stanford, 10 miles from the Google headquarters was investigating these same areas. We published an archive paper and then learned about theirs, but they did a very similar series of investigations and some of the same observations. Okay, so that's the background. So what did this Green AI paper say? What they said, we need to reduce both the cost of ML training, or ML overall. ML training is the most computational piece, and the environmental impact. And so they refer to that. If you're doing that, that's what they call green AI. And then if the other one was red AI. And they started this Struble paper. And then they say in the paper, well, it's pretty hard to actually measure energy and CO2 emissions. Why don't we just use floating point operations as a proxy for environmental impact? Well, if you're talking to a computer architect like me, optimizing for flops isn't necessarily going to have the desired effect. It's a lot better to measure. That's kind of the book that was mentioned in the introduction is called Computer Architecture, a Quantitative Approach. And a big part of quantitative is measurement. So this next slide illustrates that. Let's see what happens. Oops, back. Hold on. I only looked at the first slide. Let's see. Okay, that one is there. Next slide. Like there's a little bit of a latency or a long latency. Oh, there we go. Okay, there we go. Okay, got it. All right, and so what this axis is flops, floating point operations, to do the whole training run in this case. And we're looking at two different models. One's called Transformer, and then there's a version that is a result of what's called a neural architecture search. They found a more efficient version by searching for it, and that's called Evolve Transformer. And so the x-axis is how many floating point operations to train it, and it's measured in 10 to the 18th, so exaflops. And then this carbon emissions, the carbon CO2 equivalent emissions is on the y-axis. And so when you go from transformer to evolve transformer, it reduces the floating point operations by a factor of 1.6, and that saves a factor of 1.3 in carbon emissions. But that change in the model is kind of modest when you look at the overall change. It's more than a factor. There's another factor of 50 that we gain by changing the hardware in the data center and energy mix. So this kind of, the only purpose of this slide is point out is, well, there's something more important going on here than just floating point operations. So we think, unlike what the Green AI paper says, just reduce flops, we don't think that's the right thing to do. We can look at a lot of other things, and that was kind of one of the surprises of this document. And so what we learned on this journey was ML practitioners can improve their carbon footprint by a factor of 1,000, kind of shockingly. So first about the model matters. We just saw that if you change the model, you can reduce that by a factor of 1.3. It's actually much bigger than that. As you'll see, if you go from dense models to sparsely activated models, you can save about a factor of 10. To me, the biggest surprise was the location matters a lot. So I had these other people who wrote earlier papers had pointed out, some of them had pointed out that there's big differences in energy consumption or the carbon offset for a kilowatt hour if you're in Asia, say, versus you're in Europe, that there's big differences there. But we found factors of 5 to 10, even within the United States, even inside of Google, these factors of 5 to 10. That was certainly a big surprise. I'd done work in our textbook about data centers, so I knew that that data centers could be much more energy efficient, factors of 1.4 to 2, but not everybody knows that. And that the accelerators not only made things go faster, like the TPUs of Google's TPUs, but they saved a lot of energy. So when you multiply that all together, you could have this factor of 1,000 impacts, that's kind of, I'm giving you the bottom line. As part of doing this paper, I learned a whole lot. I thought the CO2e just meant carbon dioxide emissions, but no, it's equivalent emissions because you have to factor in the greenhouse gases as well, and that's how they call it CO2e, and that's for methane and nitrous dioxide or other greenhouse gases. You have to factor that in. And in this journey, we uncovered lots of misunderstandings. I gave this talk originally inside of Google, and Googlers are, ask a lot of probing questions, and there's a lot of misunderstandings about energy efficiency and whether it's a zero-sum game or not like that. So I'll go over that too. And then just I'll give a couple of units here that. So there's kilowatt hours and megawatt hours. That's the small and large one. Of course, megawatt is 1,000 times bigger. Kilograms, but there's this other thing I actually didn't heard of is metric tons. That's often the way it's measured, which is just 1,000 kilograms. And then to keep things in perspective, I'll use airplane travel, either and using the United States. So a round trip for one passenger or for the whole airplane, depending how big it is. And typically, on average, planes are 85% occupied. So that's, say, 150 passengers or so. But I'll use those. All right. All right. Wait for the electrons. Okay. So I'm going to show you the three things that we did, which was this case study of evolved transformer to evolved transformer. I showed you a preview of that in the prior slide. This was the study that Emma Strubel's paper looked at, so that's what we'll do that. And then there's been a lot of news in the press, a lot of interest in these very large models, the natural language processing models. Probably the most famous one is called GPT-3, which was in headlines of papers around the world. It impressed a bunch of reporters. But Google also did some large models. And basically, these large models go from hundreds of millions of parameters or weights to hundreds of billions of parameters or weights. So this factor of 1,000 increase in the number of parameters, and it has led them to do some amazing things. Well, what's the carbon footprint of that? What's the energy consumption? And then the actual paper that the Green AI paper cited, the Emma Strubel paper, on investigation, we found there were some mistakes in the paper. It was about almost a factor of 100 too high, and so we'll kind of explain why that happened. Some of it was because she was using GPUs and average daters, but some of it was just a misunderstanding of how the algorithms are done. And then I'll cover more misunderstandings and then open up for questions. Okay. The case study that we did is going from transformer to evolved transformer. And the speed up there is like I said before, 1.66 fewer floating point operations. And a lot of people in machine learning think the right thing to do is to minimize floating point operations. It's loosely correlated performance, not the same thing. As you can see, it's 1.6x flops, but it's only 10% faster on GPU of that era. The GPU, when this was done in 2018, was NVIDIA's P100, the Pascal GPU. And it's about 30% faster on the TPU of that time, TPU V2. So let's say it's about a factor of 1.3. So that's the model itself. Next step, I think, is what about the hardware that it runs on? How big a difference did it make going from the GPU to going to the TPU? So for the transformer, the original DNN, it was about a factor, the performance per watt, which of course matters from the energy perspective, is between a factor of 5 and 6. It's about 4 times faster, but it uses 30% power. So the performance per watt is about a factor of 5 or 6. For the new and improved algorithm, evolved transformer, it's about a factor of 6. Again, the TPU now runs at 5 times faster and about 20% faster. So the performance per watt is about a factor of 6. So, and then we'll talk about, so that let's say it's about a factor of 5 better. So going from a GPU to a piece of hardware dedicated for it gives you this factor of size. Why is that? Well, actually what companies, vertical companies, hyperscalers like companies like Google and Amazon and Microsoft, what they care about is not just performance, they talk about cost performance. And the actual cost they talk about isn't just the cost to buy it. It's what's called the total cost of ownership, or TCO. So total cost of ownership includes paying for it over time, the electricity it uses, and all that. So a paper that's going to be presented next week at the International Computer Architecture Conference that's on that to you is going to point out that these TCO and performance per watt are amazingly well correlated. The correlation coefficient is 0.99. So because we're doing the right thing from Google's perspective of improving performance per dollar of TCO, that also improves performance per watt, which obviously reduces energy costs and carbon emissions. Okay, so that was, say, a factor. We had a factor of 1.3 for the model and a factor of 5 for the hardware. Next up is the data center that these things are located in. So the data center is the cloud, which is, as we know, is just remote data centers connected over the internet. So how do you measure a data center energy efficiency? Well, a very popular metric is called power usage effectiveness, abbreviated PUE. That's basically the energy that's so-called wasted in the data center. So power comes into the data center. How much do you lose before it gets to the computers that are using it? And so in the United States, the average was, 50% overhead is 1.5. In the United States, the average is 1.58. 2 years ago, 1.59 last year. So Google's data center, which they work very hard to lower, and so do other cloud companies, the average is 1.1, so that's a factor of 1.4. Now, Google has claimed that actually their data centers are maybe factors of 2 more efficient than what you'd have at a university or at a business, but that's based on improving the utilization of the computers that are there, that they're not sitting there idle. It's kind of like a book in a library gets used more than a book that's put in a home. Similarly, a computer in the cloud gets more utilized, so it's not just sitting there idling, wasting power. But it's hard to measure the utilization. So for this paper, we'll just use the factor of 1.4. Okay, so that's, let's see, it was 1.3 for the model, factors of 5 for the hardware, a factor of 1.4 for the data center. Now, what about the energy that you use, that the data center uses? How much does that vary? And this, like I said, was to me the biggest surprise. So the US average is a little less than 0.5 kilogram per kilowatt hour. The data center where this Evolve transformer was run is less than 1/10 of a kilogram, a factor of 5 less. This is compared to the US average, right? Why? Well, it turns out, and if you want renewable energy, it's fine when the sun is shining, but what about at nighttime? Well, it turns out in the Midwest of the United States, where it's flat, there's tremendous wind day and night. So Google's actually, Iowa is a pretty good place to have a data center. So Google, I think while we were working on this, made an announcement what their goal is for this decade. And the goal is by the end of this decade for all data centers and all their offices to be 100% carbon-free energy. So I think the reason Google made that announcement is they looked at the trends that were going on and they believe they can get that way. I think Google in 2007 said they were going to do complete carbon offset. It was one of the first companies to do that. So they projected they would do that, and they have succeeded. So their goal is to, they say, decarbonize the grid every hour where they operate. And so what they're actually doing, if you, traditional carbon offsets, as I've learned, there's actually a bunch of rules if you're going to do traditional carbon offset. And what they say is, okay, if you do carbon offset, it has to be in the same continent. So you can't count Europe versus North America, but if you're on North America, that's fine. But what that means is in the south of the United States, in the middle of summer, a megawatt hour there, you can offset it by taking, in the winter in Canada, it's a lot easier to have renewable energy in the winter than it is in the summer, but that counts by the rules, the traditional rules of carbon offset. So not everybody's impressed with that. So Google's tried to step that up and say not anywhere in the continent, but actually on the same local grid, and not anywhere in the same year, but in the very same hour. So Google has to figure out tries to get carbon-free energy 24 hours a day, every day of the week, in wherever they're operating. So that's this kind of more aggressive goal. And so in Iowa, that was how they were able to drop the energy. When this model was trained, its carbon footprint was improved by a factor of 5. Now, next slide is going to try and put all those 4 factors together. But when you multiply it out, the better model, the better hardware, the better data center, and then the better energy footprint, it's more than a factor of 50. This is just this one example, a factor of 56, and those shows you all the steps along the way. So there's a factor of 10 in energy reduction, and then a factor of 5, as we talked about. So that's the first case study right there. This is an example of going through. So if you're an ML practitioner, what do you have to do to be able to keep track of all of this? Well, you need to know, ML practitioners They pay for the number of computers they use and how long they run. So they already know the hours to train and the number of processors. And so in terms of kilowatt hours, you need hours to train, number of processors. Then you have to figure out the average power per processor, and then the PUE, which is often published. And then with the kilowatt hours, you multiply that by the average number of CO2 emissions per kilowatt hour, and then you get the total carbon footprint. So you already know hours to train a number of processors. Everybody knows that. And Google and Facebook publish their PUE for all regions. So for any data center, you can just look that up. And if you can't do that, you can use the average of where your country typically. What we did to do the average power per processor is actually measure it while it was running. That's the best thing to do. Another thing that you could do if you're using the same hardware we used in this archive paper, which is TPU v2 or v3, or NVIDIA's Cal GPU or their voltage, you could use the data that we measured in our paper that you can see the standard deviation is pretty tight. So that would probably be your estimate. Best is measuring. Next, you can use that. Subsequently, what I learned about is there are two emissions calculators. So there's two groups that built software that try to help you calculate this yourself. You tell it what hardware you used, how, the top formulas there. You tell it the pieces, how many hours to train, how many processors, and it'll guess the average energy and guess the average power and guess the PUE. I'll show you how accurate that is. It's not terrible, but it's not as accurate as the other way to do that. I'll show you that later. Now, as I said, this really shocked to me about the location matters so much. When I gave this talk inside of Google, one person asked, well, what's better about Taiwan or Oklahoma? Oklahoma is tremendously better. So that already as a result of doing this talk, Googlers started using the more efficient data centers. So I think as this information gets out, that's certainly going to happen at Google, and I expect other places as well. They'll start looking at where you can run. Because one of the things that's interesting here. So what's hard to do in machine learning? Well, changing the model is pretty hard, right? You already have a model that works. Maybe if you're going to start over, you'll change a model, but changing the model isn't trivial. Changing the hardware it runs on. If it's running right now on a GPU, do you really want to take the effort to port it to TPU? Will there be any problems there? We think it's easy to do, but maybe not. The easiest thing to do is to change the location. The cloud is if you're at Amazon or you're at Google, where you run it is very easy to change. That's the easiest thing to do in the cloud, and that's one of the biggest factors that are there. So that's, again, one of the surprises here. Okay, so what about the second case study? Well, there's been a lot of attention to these giant models. My colleagues in machine learning, once the GPT-3 results hit the newspapers and everybody was raving about them, and we have large models too. So what are the large models? So GPT-3, what is the big idea of GPT-3? The big idea is big. GPT-2 had, I think, little 1.5 billion parameters. GPT-3 has 175 billion parameters, and it did some pretty amazing things. Right out of the bat, you could get it to do things without separate training. Google had 4 other large models that it was working on, and you can see the y-axis here, I didn't say that, is years to train on an accelerator. So years, right? So these are hundreds of years on one accelerator. This is about 400 years here. These are all natural language models. Mina is a chat robot. T5 does there's 5 T's in it for how it does the text thing. And then there's these 2 models over here, which are G-shard and switch transformer. These are dense models. So the matrix are dense. These are sparsely activated models. It's using less than 1% of the tokens during translation are activated, where this is 100% of the tokens are activated. And as you can see, the years to train is very different from these two. So that's when I said the model makes a big difference here. So sparsely activated, a lot fewer years. And of course, that's going to turn into a smaller energy footprint. So this next slide is going to show it both on a linear scale and a log scale of the differences between all these models. It'll show you the number of parameters, years to train, the energy consumption, and then the CO2, actual carbon offset. And here are the two sparsely activated ones, and you can see it's about a factor of 50. So it's many more parameters for this one, right? It has 4 times as many parameters for G-Shard, 4 times as many parameters, which is one of the figures of merit, but about a factor of 50 less time to run on accelerators, about a factor of 50 less energy, and a factor of almost 150 better carbon emissions reduction. Because it was running in a more efficient place, running in Iowa rather than running in the U.S. average. So these are, giant factors that we see here. Okay. I think that's it for the large models. So I think next we're going to talk about the search. So this was the paper. The paper that was studied by Emma Struble was actually a paper that was done by Googlers, David So and Kwok Lee et al. So the Struble paper estimated that this neural architecture search, trying to find evolved transformer from transformer, was 284 metric tons. But that was incorrect. It was actually a little over 3 metric tons. So there's a factor of 88. So what happened? Well, 2 of the factors were because Struble didn't have access to Google data. So she guessed what it would be in the average US data center, because she didn't know which data center Google ran on or what the energy consumption was there, and didn't know how energy efficient the TPU was, so she used the GPU. So the Google data center was a factor of 1.5, and running on TPUs was a factor of 3.3. It wasn't a factor of 5, like I said earlier, because she had a different estimate for the energy. But when you put that in, so that brings it down from 284 to 59 metric tons, the estimate of using the Google data. But there's still this factor of 19 that's missing there. Why is it still too high by a factor of 15? And the reason is that when my colleagues did this work to try and discover a model, what Emma Struble didn't realize is they didn't use the full transformer to do that search. They didn't use the full DNN. What they used was a small proxy cache, which was much faster and much more energy efficient to explore the space. So they explore the space, they do the search with this very simplified model to find a good spot. And then when they did find a good spot, then they did the full training. So she thought they used the large model the whole time. So that's what led this factor of 19. Now, it was hard to figure that out from the paper that they were using a proxy. You would have had to ask the authors to do that. So it's hard to figure out in retrospect. So I think for us, the bottom line is estimating the energy impact and the carbon footprint is very hard to do retroactively by somebody other than the authors. The best people to do it is the authors. They know things like we use small proxy. They know what hardware they use. They know how and so it's best if it's done when the paper is submitted, not trying to figure out retroactively, and which is, explains it, this error, Emma Struble tried to do the best they could. They didn't have access to all of the information. It's best if the authors do that. Okay, so that's the kind of the 3 things that we did. But then, like I said, when we gave this talk internally and have talked to other people's, it's revealed a lot of misunderstandings, some of which, I also had this misunderstandings. So first is this confusion about neural architecture search, which was the subject of the Struble paper. And the confusion is that a neural architecture search is the same as training a model. That those 2 things got mixed together. So to try and explain by an analogy, suppose you're trying to produce an LED light and you do a supercomputer simulation to try and make it more efficient, to reduce the energy cost of the light bulbs. Well, that seems pretty likely to be a win for the environment. But the confusion is a little bit like you would say the supercomputer simulation is the energy cost of the LED light. But that's one's a research thing and the other thing is how you produce it. So neural architecture search is done once per problem domain and architectural search. And you can reuse those results a lot. So if you think about the energy savings of evolved transformer over transformer, if you used it 4,000 times, it would pay for itself. So in fact, or if you ran it on a bigger model, right? If it took longer to run, it'd pay for itself. So in fact, it's already been paid back just using Google's example. So the MENA one I talked about before, it used evolved transformer instead of transformer. And so it's saved 15 times the energy of the neural architectural search just for the MENA. And then because this data gets shared with open source, lots of people used it. So an example of a related search called EfficientNet is on GitHub, and it's been forked 4,000 times. So the use of a neural architecture search gets reused a lot. It's not the cost of every single training, and besides it being too high. So that was that misunderstanding. Okay, let's see what's next here.
We have a question from Ian O'Connor in the chat, who cannot stay until the end of the talk.
Okay.
Okay, so I will read the question. So he is interested in understanding the importance of matching the theoretical model to the hardware architecture. How far can this be taken?
Matching the DNN model to the architecture, hardware architecture? Yeah, that's a really good question. The paper I cited in there is called AutoML. It's automatically searching the space to try, and what it's doing is exactly what that early result is, what a lot of machine learning people do well. I think the algorithm run better if I reduce the number of floating point operations, but that does not translate into performance. What the real challenge is today for computer architecture perspective isn't the floating point operations on the chip. We know how to do that. The hard part is getting things off and on the chip, going to memory. So with the paper I cite there by Sheng Li et al., they try to improve, they actually increase the floating point operations for the algorithms. They double the floating point operations for the algorithm, but they're using the memory system more efficiently, so it runs twice as fast. So it's twice as fast, which would reduce the energy consumption by a factor of 2, even though it uses more floating point operation. So it is exactly what you said, exploring the space of DNN models, not only to improve the quality of the result, but to run more efficiently on the hardware, underlying hardware. And they're doing this automatically. So automatically exploring the space, factoring in how fast it runs, as well as, as the quality improvement. So you optimize 2 parameters rather than 1. But yeah, I think that's, they got, I said, factors of 2 right there. So that's just a software change. So no hardware change, they get factor 2. So it's a really important factor. Okay. I guess there's time between the slides. Maybe I can slide in one question between your slide. And then what I noticed, when I talk to my colleagues at Berkeley, they're pretty skeptical. So why is this for-profit organization trying to save energy? So the reason is saving energy saves money, basically. So why do they do better DNNs? Well, the algorithms train faster. That makes their engineers more productive, and it saves energy, and energy costs money. So and when you save energy, that also lowers CO2. So that's why they do better models. How about why are the data centers more efficient? Kind of the same arguments. They're more energy efficient because that reduces energy, which saves money, and it also lowers CO2. And why about the accelerators? Same thing, right? It goes faster, which makes their engineers more productive, and it saves energy, which saves money, which lowers CO2. So kind of there's this old Ben Franklin saying that time is money. Well, I think in this modern world, you can say energy is money. So companies, want to save money, so they save energy, as well as they'd like to be good corporate citizens. If you don't buy that, you buy the for-profit organizations want to save money. All right. I haven't remembered the order of my discussion points. I'll have to wait. I'll be surprised. Let's see what it is. Okay. This led to, when I gave the talk inside of Google, people asked all these kind of pointed questions. which indicated this misunderstandings about how energy works. And kind of fundamentally, they thought energy consumption is a zero-sum game. So basically, if Google uses clean energy, everybody has to use dirty energy, and that reveals a lot of misunderstandings. Like I said, this big surprise to me was this factors of 10 difference in based on the location. But the green energy use is not a zero sum. First of all, data centers themselves are not fully utilized. So the idea was, well, if we for ML we use clean energy, then that shoves other tasks to use dirty energy. Now that's not the way data centers work. Data centers are actually over provisioned so that they can handle the peak loads, at a very critical time like Christmas or whatever the time of year, depending on what they're doing, maybe for other holidays. That's not, so they actually have more hardware than is used, so it's often can be idle. So using clean energy for some tasks doesn't necessarily mean the others have to use dirty energy. Another idea is, well, you're buying more hardware, but you can't be able to fit that hardware into these nice places like Oklahoma that have good nighttime winds. Actually, no, they do. They plan in ahead of that. It's kind of like a college campus. You don't buy one building, you get a lot of land. So for the next century, you can grow the campus. That's the way data centers, they buy a lot of land and they can add buildings as needed. So as Google has become aware of this differences of locations and they're trying to get their energy flip around, they will grow more in places that have more renewable energy. And they have the space to do it. The other fallacy is renewable energy is fixed, and is both fixed and can't grow. It's actually not. Renewable energy varies tremendously during the day, depending on the time of year. The solar energy, depending if it's cloudy or not, they can be much more solar energy than can be consumed. And similarly, in the nighttime winds, they can often have an excess of renewable energy that's not being consumed. So if you're using it or trying to use renewable energy, doesn't mean you're forcing other people to use dirty energy. There are often times a day where there's more renewable energy than they know what to do with. And then growing, kind of what Google has done with its carbon offsetting, is giving money that's used to buy more renewable, to build more renewable energy sources. I think the paper says it was, as of 2019, it was like $7 billion invested in renewable energy. So right now, this virtuous cycle where they're taking the money, going to the bank, getting loans, and building more renewable energy, which I think is how Google projects that if this trend keeps going, by 2030, there'll be a carbon-free energy 100% of the time. It's not fully utilized. I think I just said that. And then this other thing about, if you're, that's great when you're running in Oklahoma, but what if you got to train everywhere? No, you don't have to train everywhere. Training can be isolated to a few locations. Now, when you're doing inference, when you're trying to use the results of the training, that really does have to be everywhere because you have to be close to where the people are to reduce the latency. But training's not like that. Training can be done isolated. And in fact, training is done basically on supercomputers that Google builds, these TPU supercomputers that have 1,000, or the most recent one has 4,000 chips in it. And so it's okay if training was just being done in a small number of energy efficient locations. And fortunately, when we wrote this paper, Google's in the process of deploying the next generation TPU v4, and the first, where are they going to deploy it? Fortunately, everybody they're going to put a lot of them in Oklahoma, which has this strong, even better than Iowa. It's even windier there. So that was fortuitous that the plan was to put them there. And I don't think people realized how significant that was going to be. Yeah, I often talk too fast. This has a very relaxing, calming effect on my talks. Then there's some misunderstandings about thermal design power in peak flops. So from a computer architect's perspective, talking about peak performance as a way to measure performance, just like didn't you take a course in computer architecture? So This shows the TPU v3 in the red line here on the left. TPU v3 and the GPU have almost identical peak performance. But the blue bars are the actual measured performance in floating point operations. And you can see, although they look exactly the same in terms of performance, in terms of peak, basically the TPU v3 is about twice as fast in terms of floating point operations per second. Another one is trying to measure power, because you're trying to do performance per watt. That's the figure of merit here. Well, it's hard to measure power. So what people are tempted to do, and what the Struble paper did, is use what's called the thermal design power, TDP, because that's listed. Now, what I've learned since then is every company calculates thermal design power differently. There's no universal standard. So Intel, NVIDIA, Google, they all do it differently. So what matters is actual power usage. And it's actually not just for the processor chip, it's for the whole system is what matters. So the red line, again, is the TDP per chip, and the blue bars are what we measured is the system power on average per accelerator. And you can see that there's a big difference in TDP, but the actual measured power is pretty similar. Maybe TPUs are slightly less. So if you multiply those two things together on the next slide, you get performance per watt. What happens is if you use just the peak power and peak performance, it looks like the GPU is about a factor of 1.5 times better. But if you use the measured power, which is the real thing, they switch roles. So the TPUs are on average about a factor of 2 better than the GPUs. So basically the lesson of all this, it's really important to measure things rather than just look something up. Right. Let's see what's next. I said there were, one of the things one reason we did the paper in archive is in case there's stuff, because we were kind of new to the area, that maybe things we hadn't heard about, that we want to amend the paper. And this was an example of that. We had heard about the ML calculator. That's the red bars here. And so we compared what the ML calculator energy estimates were, where they guess the PUE and they guess the energy mix. Versus our paper. And then we subsequently learned about they're not the only calculator. There was something called Green Algorithms, which also has a calculator. So the red bars are the first calculator we knew about. The green bars are the second one we heard about. Basically, it varied from it was about half of what the estimates are to a factor of 1.5, or for the ML calculator, or a little under it to more than a factor of 2 off, with the geo means being about 0.9 or 1.5. And it's off the slide here, but this is just what is called, I would say, is the gross CO2. That doesn't factor into these things that Google is doing about doing the local 24 hours a day thing, which can be factors of 5 or 10, and the calculators don't capture that. So it's best if you actually measure what your energy footprint and carbon footprint is. That's the best way to do it. But if not, you could use these calculators that are not as accurate, but it'd be better than nothing. And as Emma Struble's paper points out, and others have pointed out, and the Green AI paper point out, even if data centers eventually, or cloud companies eventually get to carbon-free energy, reduce it dramatically, that's part of the problem. But we also want to reduce the cost of training. If only really big companies can run on really big computers to do training, that's not going to be optimal for the field. We want everyone to be able to participate. So working on ways to reduce the cost of energy would be a really great, or reduce the cost of training would be a very effective use, a very important direction to go. So we echo the remarks of others that'd be great if people are working on reducing the cost of training. Another concern was, well, Google has these really great data centers, and what happens if you don't work for Google? Well, it turns out all of these companies want to rent their computers to you. So Alibaba Cloud, Amazon Web Services, Google Cloud Platform, Microsoft Azure, all these people have these very efficient data centers. Alibaba, Amazon, and Google have designed custom processors, both for inference and training, that they will rent to you. So both the data centers and the hardware is available to rent. So anybody in the world can use it. It's not just these few number of companies can do that. And then I think what's next is talking about some of the, so I've been spent like 90% of the talk talking about all the downsides about it. There's one more thing here. People are worried about the cloud, right? Boy, the cloud's growing fast. The energy footprint of this must be growing fast too, which kind of makes logical sense. But what people don't appreciate is the cloud's been around for a while, right? For, I think, Amazon started in 2007 or so. So it's almost 15 years of the cloud. But what happens is servers wear out. We don't have servers from 15 years of still operating. They break. Typically, a standard accounting practice is to fully amortize the cost of a server over 3 or 4 years. So maybe they stick around a little longer than that, but they don't last a decade. So you'd think what's happening, if the cloud is growing fast, then the number of servers shipped should be growing fast. But when we look at the data, that's not the case. It's only going up about 3% a year. So how do you explain that? How can the cloud's growing a lot faster than 3% a year, but the number of servers isn't growing much faster than that? So what's happening is, and there's this paper in Science magazine that made this observation, is people are deciding, well, I'm not going to buy servers and stick them in my university data center or stick them in my cloud. I'm going to use the cloud instead. So as we transition from buying servers and managing them ourselves to using servers in the cloud, that's increasing the utilization of those servers, and they're running these more efficient data centers. So we're actually, the cloud is not is not growing. The cloud, or no, data center carbon footprint is not growing very rapidly, even though the cloud is. So this paper in Science said, in this last decade, energy consumption of data centers has grown only 6%, despite the computing capacity increasing by more than a factor of 6. And it's because we're going from these less efficient data centers with less efficient energy sources to the cloud, which is a lot better than that. And this data kind of, for this last decade, agrees with that Science paper. Okay, now I think we're going to talk about some of the benefits. Well, so why do you want to do this training? Or how do you put it in perspective? So I said, what about these commercial jets? How do we put this in perspective? So this is what the cost is for each of these models, carbon efficiency costs. So for the 2 of the Google models, it's a quarter or a half of one of these full plane trips. G-Chart is this very efficient thing. It's only 2% of one of these full plane trips. Switch transform is about a third, and GPT-3 is much more energy consumption, but it's about 3 of these plane trips. So how do we, 3 full passenger trains round trip? That's the energy carbon footprint. How do we put this in perspective? Well, look, NeurIPS, which is one of the machine learning conferences, the last time we had a full one, 13,000 people attended, and this was in Canada. So must have been at least 10,000 people got on airplanes to go there. So, and if it was 150 people, that'd be a lot of plane trips. So I think as a result of me doing this study, I'm going to do less plane trips. I didn't understand the carbon footprint of plane trips, but I think plane trips are going to be our much bigger problem than the energy consumption there. And in fact, what I didn't realize when I started this, Google is part of the carbon offset, publishes how much energy it uses, because that's part of the accounting process for the carbon footprint. So Google in 2019 used 12.2 terawatt hours. They carbon offset, but that's how many they use. So how much is this energy here? So if we look at the bottom of the slide, that's megawatt hours in millions of megawatt hours there on the left. This is how many megawatt hours all these Google 4 models is. This adds up to less than just about 500 megawatt hours. And you can see it's round off error, right? So that's the final training run. And as people accurately point out, there's a lot of prep work that gets done before you do the final training run. So that actually, there haven't been many papers yet to talk about how much time do you prepare versus the final training run? What's that ratio? So this is an area that needs investigation. And our colleagues at Stanford have created a tool that helps you track that. The people doing the calculator are creating a tool that helps you track that. But this is data that has to be done. Now, but I think it'll be interesting to see for these very large models, since they can take a month to run on 1,000 processors. You can't afford to do this hundreds of times. Nobody has the money to do that. So my guess, it'll be like what happened with the Evolve Transformer. They'll use a smaller proxy to explore the space to try it out before they do the big runs. I mentioned that AutoML result. They found that in terms of the energy it spends exploring the space was about the same amount of energy as it took to do the final run. So it's a factor of 2. So we'll be interesting to see what the results are. But even if it was a factor of 10, that would be a trivial amount of the energy use. And only 2 of these done in 2019. So it's the actual training is a very small part of the carbon footprint for Google, which was I guess comforting to learn. All right, now upsides. So talking about quarantine and COVID-19, Google put together a search engine to help scientists find the paper that many scientists used. It used the BERT transformer model, which because it ran and partly because it ran on TPUs in Oklahoma, it was very little energy cost, like the 10th of one passenger trip, not the whole airplane, a 10th of one passenger to do that. And there are scientists who said that helped with the quarantine, which is a very good use. A second one is also a use of BERT, which is this very efficient model. And this is for doing the snippets that apply. If you use Google search, you put your answer. Sometimes you'll get the answer there. They'll give you the answer. You don't have to click on it. These are called snippets. So the BERT model really helped snippets in other languages. Most of the content on the web, or the majority of the content, or maybe not majority, the plurality of the content is in English. So you can learn from English and apply it to other languages. So that BERT model was a big help, particularly in languages like Korean and Hindi and Portuguese. And the final example is actually G-Shard itself. So you can learn, they looked at other language to English translations, or translations between English and other languages. And then this model is one of the figures of quality score. It's called the blue score. This is the improvement in quality score. And then this is sorted by languages in terms of how many resources are available. So languages like French and Spanish are where there's billions of examples. They're over here on the left. In languages that still have lots of speakers but don't have lots of examples, like Yoruba, is on the right. And what you notice is everybody benefits, and then the different lines here is how sparse it is, or how many parameters it is. So I think this dotted line is a dense model, and the blue line is a 600 billion parameter version of the sparsely activated ones. So you can see sparse, because it has a lot more parameters, it's a lot more accurate, and it's not a lot more energy because it's sparsely activated. In fact, the whole energy cost for this thing is like 3.5 passenger round trips, not whole planes, but do that. And interestingly, it really helps these languages with less resources like Yoruba even more. So, this is not my area of expertise, but, provided you pay attention to issues of fairness and bias, there's a lot of papers that we've cited there. This can really help a lot of people around the world. So right now, what Google uses is called the M4. It translates billions of queries per year in these languages like Yoruba that don't have a lot of resources that, a lot of people use. Okay, I think I am in the, wow, it looks like I'm a talkative guy. I think we're ready for the last 2 slides of conclusions. And I got 2 conclusion slides, and then I'll open it up for questions. So, it's energy and CO2 emissions are important. Lots of people care about it, yet it's hard to get right, especially retroactively. So like others, we think the authors ought to publish their energy consumption, CO2, or everything they need to calculate it to make the training costs transparent. If you're going to do something really big and computation intensive, you ought to, as authors, you ought to put that in. We think, we agree with Struble and the Green AI paper is that we should encourage work on efficiency as well as accuracy. Because, the most sustainable energy is energy you don't use. So that's good. And then let's also concentrate on costs, publish the actual number of accelerators and time to do that. Because, even if we get carbon emissions, it's still, we want more people to participate so the training can do. So since we've kind of been working on this paper, there have been two good things that have happened. That's our positive signs here, which is we participated in what's called MLPerf, which I think is the leading machine learning benchmark. And I have long advocated that we have to figure out a way to compare different systems, and one way to normalize that with power. So they are doing that now. MLPerf now has included power for their inference benchmarks, and we'll add it for training. So I think we'll start seeing this competition not only in performance, but on energy use or performance per watt, which I think would be a good step forward. And then Google recently they published their PUE for all the data centers. They recently released the percent carbon free per all the data centers. So we think that's a good sign. But then kind of wrapping this up, I kind of went into this expecting to be kind of apologetic as, gee, I'm sorry that machine learning, is doing all these things that we have, using up all this energy and resources. But it's kind of shown off that it touches a lot of strengths of these cloud companies. So typically, these cloud companies are often leaders in machine learning. So Google Brain, Google DeepMind, Facebook has a very strong machine learning group, and Microsoft Research. These are all big names in research. So they're kind of leaders in natural language processing and also fairness and bias work. So that's one of the strengths. Processors, Google, that is a leader in ML accelerators. You could argue that Google got this started commercially. They've announced 5 of these so far. NVIDIA has announced 3 GPUs that have been tailored for machine learning. And then Alibaba, Amazon, and many others are rumored. Alibaba and Amazon have delivered chips, and others are rumored to be doing the same thing. So they're doing custom hardware, the data centers. All these companies have been publishing or pushing the PUE down to be, save money and be more energy efficient. And then and Facebook and Google are leaders in the carbon emissions themselves, the energy mixes. Trying to locate it in locations that use renewable energy, and Google set this target. Okay. All right. Well, thanks for your patience. And I am ready to handle questions.
Thank you, Dave. So we have a couple of questions in the chat. Yes, from Pierre Boulet. Do you take into account the carbon impact of manufacturing the hardware?
No, good question. Yeah, I should have. In fact, I'll put that into the slide. It's in our paper, but and there's going to be a workshop next week at the Computer Architecture Conference. So we're only talking about chips after they've been manufactured. There's other papers that you could look at that try and factor in the energy costs of making the chips and recycling the chips. So we're just talking about the chips have been made. What about the machine learning impact on that? But that would be, that's not something I've studied, but I think the archive paper does have a citation to this paper that was done, I think, at Facebook that does talk about the energy costs of manufacturing the chips as well.
Renaud, you can ask.
Okay, yes. So the next question from Jan is, what about the importance of location in the federated learning context where latency is also an issue during training?
So, I'm a hardware guy. So you say there's training that relies on real-time inputs. Is that what you're saying?
Okay, he's writing. So let's see. Yes, that's what he meant.
Yeah, so I'm not familiar with that. The training that I see at Google is that's not why. This is not that. I'm not. I don't know about that kind of stuff. That's certainly not what we're spending time. What can I say? Most of the training I'm aware of is this kind of offline training, and that's why we're building these supercomputers, and it runs for weeks and days. So I think that was the thing that people are more concerned about. If you're doing, and the other thing, I should have put in the qualifications what we're not doing. We're not talking about the edge. I think that would be another interesting study. Is what about the energy carbon footprint of the edge? So what about cell phones or IoT devices that are using machine learning? I think that'd be another really interesting thing to do. We're not talking about that. In terms of distributing, if you're doing training in a distributed fashion all over the world, that would be kind of, I guess, edge-based training. And I'm talking about data center training, and we're not doing about the energy costs of making the chips themselves versus using them.
So the next question is from Alex Albani. What do you think of Jevons paradox in this case? So Jevons paradox is the Jevons paradox. So when you optimize for something like build more roads, it turns out that you get more cars, and the efficiency gain are offset.
Because I've talked this results over with other people, and they brought that up, Jevons paradox. So as a result, I am trying to figure out that answer inside of Google. I'm trying to figure out the answer, and then B, I'm trying to see if I can tell people if I get the answer. The cloud is growing, and the question is ML growing faster than the cloud is growing? And I'm trying to get the answer to that. I'm hopeful that I'll be able to find the answer and to publish it. But as this person said, until companies like Google announce what fraction of their energy use is machine learning, training, and inference, people are free to speculate what that is. I think it's, my guess is it's not going to be a big deal, but that there's this argument is the more efficient you make something, the more it gets used, so the net goes up. I think it might be a bigger deal on the edge than it is in the data center, but I think it'd be really interesting to do this same kind of study for the edge to see what's going on.
Okay. There is one question from Laurent Bézassier. Your numbers seem mostly related to training of models. I'm wondering how your findings transfer to inference when models are deployed for users at scale.
Right. So the difference is for inference, it has to be, you can't just do inference in one spot. It has to be near users. So you're going to, there's big differences, as you can see, if you look at the Google thing. Asia tends to be much worse in terms of energy. Carbon footprint is much worse in Asia. The percentage of carbon-free energy, and this, or Australia as well, that's not been a focus in that part of the region. So if you're going to do the inference around the world, you're going to be in areas where the carbon footprint is much larger. I think, and then the question is, what's the ratio of inference to training? Because training takes forever, right? It takes months on thousands of computers. Inference takes milliseconds, but you're serving lots of things. So lots of people doing inference, a few people training that take a long time. How does that balance work out? So when I try and get the answer for Google over the last 3 years, what percentage of the carbon of the energy sources has been for machine learning, I'm going to try and get both training and inference as a sum, because I think if we tell you here's how much is training, they'll say, well, but how much is inference, right? So we're going to try and figure that out, but we don't have the data yet, so I don't know what that's going to be. But it could be that inference is much larger than training. I mean, that could certainly happen, but I don't have data to share on that.
So the next question is from Jacques-Olivier Klein. He asks, do you think that edge computing is or would be less efficient than cloud computing for machine learning? Energy efficiency of optimized architecture versus near sensor computing. What is best in your opinion?
Yeah, like I said, I'm not quite sure how I got into this. Somehow I guess my job at Google, I get to kind of work on, I have a lot of control over what I got to work on. Somehow I got intrigued by this problem. I would be really interested in the edge side of it. The difference is batteries, right? You're charging a battery overnight, and then if we talk about phones, I guess any kind of edge device probably has a battery. So how do batteries affect these calculations? How much energy do you use charging a battery? How much do you save by not, if the device just sits there, the battery energy decays versus use. So it's more complicated. So I'd be really interested to see how this turns out. There's 1 billion cell phones every year, but boy, they have limited power budgets. You can't burn people's hands. I think they try and do everything in 3.5 watts. The hardware is very energy optimized. Probably the battery life and just the temperature is very controlled. It's a very rigid budget. There's a lot of innovation to be energy efficient. They have ideas, what they call big processors and little processors. So when you're being idle, instead of running the fast processor, they have a little tiny one that's very energy efficient. So it'll be interesting. It'll be a really interesting study. So, but I think I'm unwilling to make a guess until we somebody does a study or we do a study. I think it'd be really fascinating to find out how that works. You'd think with 1 billion devices, there's so many more of them, even though they're low power. You'd think that would be the bigger deal, but how does batteries going to mess this up? So I think it's, as engineers and scientists, I think we have to wait and see.
Thank you. The next question is from Fred Petro, who thanks you. And do you know if people at Google are looking into how to learn with non-effective and low bit size, which will allow for optimized hardware acceleration?
With lower bit size, is that what?
Yeah, low bit size and non-floating point numbers.
Yeah, it's a very what's really interesting. If you look at the history of computer architecture, which I'm ever so interested, computer architecture in the beginning was computer arithmetic, right? They're trying to figure out how we're representing numbers. Is it 2's complement or 1's complement, integers, and then things were different word sizes. They'd be 12-bit and 24-bit. So it took us a while to end up with these bite-sized things and 2's complement integers, and then the floating point was all over the place. So surprisingly, I'm surprised because I thought once my colleague at Berkeley and Turing Award winner Velvel Khan developed was the force behind the IEEE floating point standard, we wouldn't be talking about floating point in the future, but machine learning has brought that all up. So Google has pioneered something that's called brain float or B-float, which is a new 16-bit floating point format that's much better matched to machine learning. I'm surprised I'm associated with a new floating point format that's not part of the IEEE standard. And then a big way to get energy efficiency is to use fewer bits, right? If the multiplies are smaller, there's an n-squared effect on the multiply. So this is a very active area. So for inference, it certainly looks like there's sometimes, this paper that's going to be at the computer architecture next week is about TPU, we call it V4I for inference. And it talks about the energy benefits of using integers, but there's times it just doesn't work. There are tasks for which you have to have floating point, and that's one of the surprises of that paper. The paper is called 10 Lessons Learned from 3 Generations of TPUs and How They Apply to TPU4i. And one of the lessons is you can't always do inference in integers. Now, and the flip side of that is, what about using integers for training? So far that's been kind of a research area. One idea is, if you train it in floating point, can you then the results do inference in integers? That's kind of extra work. So there's people are interested in the idea that you train in integers so that when you do the inference, you don't do extra work there. So it's an active area. Still, for production at Google, most people are doing things in floating point because, the machine learning people are the critical resource, and for them to explore this space, it's easier for them to do things in floating point, but it is an area. And again, all my experience is inside the data center. If we get to the edge and you're doing training on the edge, then because of the more constrained energy resources, then the integer calculations are going to play a bigger role, and people will see that. But you see papers not only going from, instead of 16-bit floating point numbers and 8-bit integers, you see 4-bit integers, 2-bit integers, and even 1-bit integers. So this computer arithmetic for machine learning is a very active area where people are trying to both speed up calculations and save energy.
Do we have question on YouTube?
There was just one question on YouTube, but I think it was already addressed by Dave, because it was someone, Yannick, wondering if the footprint of the construction of the windmill and other infrastructures were taken into account in the results. But I think Dave already addressed that point.
Yeah, you should talk to somebody else about that. I mean, I think the windmills, I assume they have long lifetimes, but I've never gotten into that area, so I shouldn't speculate. Okay, how about I tell you my life story? If you haven't given up, I think what I'll do is switch over to sharing slides. Do I have to close this one? Maybe I close this one.
No, just share your screen.
I'll just share my screen. Okay. Right, Chrome tab. My story. Okay. All right, hoping you can see that. So in terms of giving advice, if I was getting started, if the advice I would give to somebody, like I said, I think I started graduate school more than 50 years ago. The advice I would give, of course, this is kind of English oriented. So starting from the bottom right, I think I had to learn how to write. I really enjoy writing now, but that's not how I started graduate school. But the best advice I've seen is this book, the classic book by Strunk and White, really concentrated on brevity. And Strunk cared about conciseness so much. His book is really small. So it's a little tiny book, and it's not very many pages. But in terms of, I don't know if it's good advice in writing in French, but it's really great advice for writing in English, and I'd encourage you to read that. As it turns out, computer science is not done primarily by individuals. Computer science engineering is done by teams. So learning how to manage, it's not something they teach you in graduate school. You have to kind of figure that out on your own. But I think this book, again, another skinny, small book, The 1 Minute Manager, gives advice about how to be a good manager for the people who work for you, as well as being a good manager from the people who work above you. And it talks about managing up and down. And that's the management advice I got. This book on how to be productive, it's not a skinny book. It's a pretty long book. I have read part of it. I think it's really important to figure out how to be productive. Before we started, we talked about trying to find the time of day where you're at your most productive and to protect that time. For me, I get up early in the morning, and if I can get 2 hours uninterrupted in where I can concentrate, that's really a pretty good day. And then it doesn't matter the rest of the day. You can't write all day long. So try and figure out ways to make yourself productive, making lists and things like that. There's some well-known techniques that can make you more productive. I thought I started graduate school not so productive and had figured out over time how to become more productive, watching other successful people. But you can also do that reading. If you're going to be, a scientist or engineer, part of what you're doing is coming up with ideas and trying to get people to use them. So this is a really old book by Carnegie of Carnegie Mellon University and the Carnegie Foundation in the United States. And he wrote this book on how to win friends and influence people. Yeah, I don't know how old the real book is, but the advice was still pretty good. It certainly influenced me about how you do that. And then, as I'll say if you're going to have a career, you ought to be happy. So kind of psychologists up until, say, 25 years ago, just studied crazy people. Those are really interesting. Wow, why is this person psychotic? Why is this person schizophrenic? That's what all the excitement was. Then somebody kind of had this radical idea 20 years ago. Well, should we study why people are happy? And maybe we can figure out why normal people are happy and how to make people happier. So here's a book. This actually was written by a person who used to be the head of the American Physical Association. So he was like a president of an organization like that. And they've studied how to be happy. And so I would say if you're starting a career, you ought to read about that. It's having friends, having family, finding something you enjoy doing. And, I think if you can find something you enjoy doing and get paid to do it, that's pretty good. But you could read about how to be happy and help you figure out what you want to do. Okay, so that's my book advice. How did I get here, right? Like I said, I tell this story because people think if you've been successful, you haven't had the problems that I've had in grad school. So let me tell you my story. So I graduated from high school more than 50 years ago. I'm an accidental computer science student. I was actually a wrestler in high school and in college, and a math major in high school. I did well in math, so I majored in math. And then my favorite math teacher encouraged me to study math, so that's what I studied in college. There was no undergraduate degree in computer science yet. Now, within my family, no one in my family or my ancestors had ever graduated from college. So my goal was to be the first one in my family to graduate from college. And if I got a bachelor's degree, that was success. That was the goal. So what happened? Well, I mentioned wrestling. That's me in the back. This is the wrestling team. This was a pretty good team. We were champions of California. So what happened in my junior year at UCLA in Los Angeles, my math class was canceled that I wanted to take, so I had to find another course. And so fortuitously, there was a introduction to computer programming course. It was even only a half of a course, was in the same time slot. So I decided to take it. And no one had told me that computers are going to be the future or anything like that in high school or college or anything. I was kind of on my own. I just took it. Well, despite how primitive that programming system was, where you had these, you actually had to punch pieces of cardboard to put your program in, and then you would get these printed listings, and it would take overnight to do it. To be able to do that, it hooked me, right? And it's kind of like if you look at video games from 30 years ago, you can't believe people played them, but the people at the time were very excited about them. Well, I still, even that primitive programming had the thing where your ideas in your head could come alive in the computer, right? And I was hooked. So my senior year, I took every engineering or business computer course I could, kind of did my own computer science major, and because I'd found the thing I wanted to do in college. Very fortunately, Jean Loubert, who's French, was a professor at UCLA at the time. He had just gotten his degree was teaching, and I took a course from him. And I said kind of casually at the end of the course, I did well. And I said, boy, I'd sure rather be doing this than supporting myself going through college. My wife and I were married, and we were earning our way through. I was working in a factory. I'd sure rather be doing something in computing. I just kind of said this innocently after the course was over. So he on his own, went and found me a job on campus. He got me a job as a research assistant on campus, and as an undergrad. And then I got involved in research as an undergrad, as helping out, and then that was really exciting. And then the second thing that happened at just about the same time is I was in my very last, as a senior, I was in my last wrestling. So my last match as a wrestler, and the last period, in the last minute, I injured my knee. So the reason that was really important just before I graduated was this was during the Vietnam War. And if you were a man, you weren't going to be drafted if you finished college. But once you finished college, you were drafted and you would go to Vietnam, very, very likely. But because of my knee injury, when I was drafted, I failed the physical because I was limping at the time, and because my knee was sore. But if I hadn't injured my knee, I surely would have been drafted. And I think it's unlikely that I would have gone to into graduate school, because my wife was pregnant at the time, and she gave birth about the time I graduated. So that's probably, if I'd been drafted, I wouldn't have gone to graduate school. And so fortunately, I injured my knee. Then when I got to grad school, I asked my wife about it, and she said, well, a master's degree. I told her that doesn't take that long. And then after I was there a while, everybody in my office was getting a PhD. So I said, what'd she think about a PhD? And she said, well, if you think you're smart enough to do it, go for it. So that went fine. And then we had our first son, and then we had our second son, and we were living in the married student housing, and we were supporting ourselves on a 20-hour-a-week research assistant salary. So we were pretty poor. We would buy used clothing. We didn't own a car, even though we were in Los Angeles. And after about 4 years, the research grant ended, and I didn't have a job. So that sounds pretty bad. And it was. Fortunately, my advisor helped me get a job at a nearby aerospace company. And this aerospace company was actually designing computers to go in airplanes. So I had taken a couple of hardware courses, but not very seriously. I considered myself a software person. But because I got that job at the local aerospace company, I actually got to design hardware and build it and manufacture it. And so it was a hands-on education, and I found it really interesting. And there's pictures of my first son and my wife with my second son at the time. And then I'm an accidental student, an accidental PhD student, but an accidental Berkeley professor. So at the time in 1976, UC Berkeley tried to hire Doug Clark, who's still a well-known computer architect at the time. And so did Stanford, as it turned out. They tried to hire him, and he turned them both down and went to the Xerox Palo Alto Research Center, which was famous for kind of inventing the future of Windows system. So as it turns out, and I didn't know this, but after Doug Clark had turned him down, my wife, who had grown up near Berkeley, wanted me to find out what happened to my application at Berkeley. So she kind of forced me to call, while a PhD student, call the chair of the department at Berkeley of computer science and ask, basically, well, I hadn't heard from you. I had a couple of job offers, one at Bell Labs, but if I heard from Berkeley, I'd put that off. But what happened to my application? And so, and I was just dreading this completely. If my wife hadn't forced me, I never would have called. I would have just it would have been easiest just to not hear from Berkeley. But he said, well, Dave, you're in the top 10, but not the top 5. And so I was completely relieved. That was not as humiliating as I expected. So what I find out afterwards, he said that to anybody who called. He said, oh, Harry, you're in the top 10, not top 5. So it was just a polite thing to say. But he took my application out because my wife forced me to call and looked at it since they need to find somebody. And so one of his colleagues was going to go to Southern California anyway. So he stopped by the university and talked to me. We had a nice chat. They invited me to interview, and I got the job offer. And then this guy I met who interviewed me when I got there wanted to do a project, and I just was following his lead. And it was an extraordinarily ambitious project with not enough resources. It was designing chips, designing your own operating system, building a multiprocessor, hugely ambitious, and we didn't have a research grant. So fortunately, and unusually, about 3 years into my assistant professorship, where I'm kind of going to fight for tenure, I took a leave of absence at a computer company on the East Coast and gave me time to reflect, to think about what we're doing. This particular computer company was building the VAX mini computer at the time, which was a really complicated computer, and it was filled with bugs because it was so complicated. And I came back from that sabbatical and thought about that. I could see that microprocessor of the future, and the way that company was building computers didn't make sense for microprocessors. So what I did next was the reduced instruction set work that I did and Hennessy did and IBM had all worked on, and that caught fire, and that actually eventually led to the Turing Award. So then after that, things went pretty well. But that was absolutely not the plan. My wife is still surprised that I'm a professor at Berkeley in computer science, and I am too. We're both surprised I'm a professor at Berkeley in computer science. So what's worked? How have I been successful? Oh, okay. Well, the first thing is family first. So back when 40 years ago, when I became a professor, there's all these stresses on your time, all these people who need your time and want you to do things. It's really easy for your family to be deprioritized. So I had a little bit of time before I started at Berkeley, and I said I was going to make family first. So I have 2 sons. So what that meant was there was football, Americans call it soccer. I was the assistant soccer coach. When they went on field trips, I went on the field trips. There was what's called Cub Scouts, where the boys get together. I was the den leader for that. So pretty much I tried to volunteer for everything. So when you're kind of adorable little infant sons become rowdy teenagers, and they said, well, Dad, you were never there. Oh, we went down the list. Soccer, Cub Scouts, Indian guides, field trips. And I said, okay, well, maybe you were there. But I'm just really glad I played the family first, and we're still close today. So as I said, it's important to be happy. One of the ways to be happy is have fun. So I go body surfing. That's surfing without a surfboard. And I do that with one of my sons, and I play soccer. I love playing soccer. I do that with my other son, and we all go for bike rides. So we're a very close family, and thank God I kept the family first. Passion and courage. You might be able to tell that from my talk. I have to believe in it. If you know about Star Trek, if people watch Star Trek, so I kind of look like Jean-Luc Picard. Whoopsie, I kind of look like him. And I like to think of myself, he's kind of the intellectual captain, but that's not me. I'm really Captain Kirk, kind of this guy who gets into fights and gets all emotional and stuff like that. For me, I have to believe in what we're working on could change the world. If American baseball, they talk about hitting home runs, that's swinging for the fences, and rather than just safely getting on base. I guess for soccer, it would be taking, what's the soccer analogy? People who are always striving to score. You're always trying to score. We're going to send everybody up. We're going to go for it. We're going to go for the score. We're not going to tie the game. We're not going to play defense the whole time. We're going for it. I need to believe that we have a chance to score. Because I'm passionate, and one of my colleagues warned me this old saying that friends may come and go, but enemies accumulate. And that's certainly the case. If you're a passionate guy, be careful not to make enemies. You went to high school, you went to college with some people, you kind of drift apart. Enemies, that doesn't happen with enemies. Enemies remember who you are their whole lives. So as far as I know, I've only made a couple of enemies over my career. So pick your enemies carefully. They're going to last a long time. So kind of fortunately, one of the guys who's probably an enemy was a guy in charge of a U.S. government agency that funded things. And so I felt like, he was screwing things up by not funding academia. So I and a person, Ed Lazowski at University of Boston, took this guy on, wrote op-ed pieces criticizing what he's doing. So not a lot of people wanted to join us in that because they feared he would be a vengeful guy, and he probably was. But as it turned out, if a lot of people, if you pick an enemy, somebody that a lot of people don't like, you can make a lot of friends. So just be careful. But remember, enemies are going to last a long time, so pick them carefully. Winning as a team versus winning as an individual. Even though I was a wrestler, my high school and college coaches believed that if we bonded as a team, we would be more successful, even though we were out there one at a time. So I just kind of believe that in my DNA, that if you can get a group of people, you can get them to collaborate in ways and you can be successful. And one of the sayings from Fred Brooks, who's a Turing Award winner, is that there's no losers on a winning team and no winners on a losing team. So if you were to, even if in soccer you would score a lot of goals, but your team lost all the time, you're not really a winner. It's the team that wins, independent of whether if all you're doing is helping out in practice, you're still part of a winning team. That's kind of, I believe that. Seeking out honest feedback and learning from it, I think that's one of the things I've done well. So if I try and share the papers, I try and talk to people. Like when I was, these results that we want to try and publish, I've talked to a lot of people about results and got feedback onto it, like about Jevons paradox. People have brought that up. I want to try and investigate that. And I think if we can get an answer, it'll make the results stronger. So now, but there's a corollary that I've noticed over my career about the honest feedback. Is what I've seen is one of the surest danger signs is somebody who thinks they're the smartest person in the room. So my list of people I know of who've done that is there's a computer architect in my field who thinks he's the smartest person in the room, and he is not a very popular guy. A lot of people don't like this guy. There's the president of one of the Ivy League colleges in the United States, one of the private schools like Harvard or MIT. He's former president. He thought he was the smartest person in the room, and he was fired for what he did. There was an energy company in the United States called Enron, and the founder and president are convicted felons, doing prison time. And I actually have a brother of an ex-brother-in-law who thought he was the smartest person in the room, and he's a convicted felon. Okay, so what's going on there? I think they're smart. I think the problem is if you think you're the smartest person in the room, you don't think there's any value to sharing your ideas with the people who aren't as smart as you. You're not going to get feedback on ideas. You think, I'm so smart, I can figure this myself and I'll go ahead. And you make these terrible mistakes that send you to prison or get you fired. So, but the most important thing, well, there's two things. Try to get feedback, honest feedback, and listen to it. And if you meet somebody who thinks they're the smartest person in the room, just run away. Just don't do anything with those guys. Another thing that happened to me was trying to do one big thing at a time. And I can still kind of remember maybe 10 years after my PhD, it was like God spoke to me. I kind of woke up in the morning and I had this saying in my head, it's not how many projects you start, it's how many you finish. This is particularly true in academia, where you kind of volunteer for a lot of things you want to work on and you want to make people happy. And some people just end up with way too many things. So once it kind of hit me, it's how many things you finish, not how many you start. I tried to do one big thing at a time. So when Hennessy and I wrote our book together, that Computer Architecture Quantitative Approach, that was the big thing we did that year. We did other things, smaller things, but the big thing was that book. When I was president of ACM, that was the big thing I did that year. And so I tried not to have more than only do one big thing a year. Now, as it turns out, because a lot of people just volunteer for a lot of things and never get most of them done, if you get one big thing done a year and over 20 or 30 years, that looks pretty productive. So I don't think I'm all that more productive. I think I'm more selective, only doing one big thing at a time. So that's what's worked for me. And then I'm a natural born optimist. And I think, reflecting on my career, it's better to be optimistic. Research often, it's not clear if it's going to work or not. And you probably are going to be more successful if you think you're going to do it than if you're pessimistic and think, this probably isn't going to work. I think it'd be better err on the side of optimism. So my story goes back to my youth as a teenager. So I had just started dating. I was 16 years old, and I found this girl I really liked. So after a couple of dates, I asked her to be exclusive, and the time we said, we talked about it is going steady is the phrase that we used. So when I asked her if she would go steady with me, she looked at me. She had dated other boys and she was also only 16. And I think she looked at me and she said, well, Dave, I don't know how to say no. So to me, as an optimist and a logical person, that sounded like yes. So I hugged her and said, great. I thought that she gave me the answer I wanted. In her mind, she said, I think, well, I'll let this guy down later. But, we've been married for 53 years now. So far, she hasn't let me down. And then, so the last part of my story, that's a picture of us at 16, and that's a picture of us recently. So when you've been married more than 50 years, people ask you, what's the secret for a long relationship? They think you're an expert on that. So we actually have an answer to this. There's 9 magic words in English. You'll have to translate it. But it's 3 phrases, 3 sentences, each of 3 words. And to make it easier to remember, since this is will let you have a long relationship if you want one, the first word is I, then you, then I. And you have to say all 9 words. There's no shortcuts. You got to say them all. So the first words are, over here. I was wrong. You were right. I love you. And you got to say all 9. It's not like I was wrong, you were right, you're a jerk. You can't do that. You got to say all 9. Okay, with that, I've given you life story advice, and I think that's the end of my talk.
Thank you, Dave. There's a question from Gentian Jacques Larry. Doesn't the modern academic system, especially US, rewarding or expecting massive publication lists, encourage the burn for singles?
Yes, it does. But early in my career, what I was told when I got to Berkeley is that institutions like Berkeley value impact. We don't care. What we want you to do is have a really big impact in the world. We want you to become a leader at something. Want your research to make a difference. So I thought that was wonderful advice. So it was okay if I like working in teams. It was okay if we worked in teams. That what all that counted was impact. And so that was just what I wanted to hear. And that's what I tried to do. Now, it's maybe institutions towards the have more self-confidence. They can evaluate impact. Now, if you have less self-confidence, then you could use just number of papers or number of citations as something you can measure, you can count. It's easier to count those things than it is to count impact. But it's not that hard to measure impact. Kind of the way academia works is you get these letters of recommendations for promotions. And if you've really had impact, lots of people know about it, and it's easy to write letters. So it was the advice I wanted to hear, and it's the advice I would pass on. Right? And you look back at a career like, I'm obviously closer to the end than in the beginning. What are the things I'm proud of? Well, some of them are papers. And but it's really the people you worked with and where you really had impact. So in fact, Hennessy and I just won the Turing Award a couple of years ago. Why did we win it? For 2 things: for our risk work, but also our book. Our book was equally important, maybe even more important, because that book at the time we brought it out really changed the way computer architecture was taught. Before that, it was kind of like a catalog description. Here's a computer, here's its features. Here's a computer, here's its features. And you kind of read the book, and then you'll kind of survey of all the computers that are out there, and then you're supposed to figure out how to do it yourself. So we made it much more quantitative. Why did we do that? We did it because we were very unhappy with the books that were out there, and we, as part of this risk work, we had ideas of this more quantitative approach to teach it. But at the time, the advice was not to write a book. It might still be the advice. The textbooks, you can't make research contributions with textbooks. You write papers. So if we'd been optimizing if we'd followed the traditional advice, we just would have written more papers and not written a textbook. But John and I thought, we wanted to write a textbook because we wanted to correct the way computer architecture was being taught. We didn't think in a very good way. And actually that turned out to be critical for, 30 years later, getting the Turing Award was doing that. So not thought, especially I think young people think they know the right way. I've met people who are absolutely convinced they know the right way to get tenure or to be successful. And sometimes when I visit universities, I've had these young people tell me, well, I'm working on this thing. I'm not very excited about it, but I know how to get research funding and I can write all the papers and I have to do that to get tenure. And then I go talk to the department chair and he says, well, that guy, it's pretty incremental work that he's doing. It's not very impressive. And then I don't know what the ending story, but that didn't sound very good. So I would, find something you're passionate about that you really believe can make an impact and figure out a way how to be able to work on that. Life's short. You don't want to be doing stuff you don't believe in. You want to have something that you care about and you can be proud of. You want to work on stuff you can be proud of, and then you want to give your chance of impact. As reflecting on my career, kind of the way I did it, I did lots of 5-year projects. Most research doesn't work out, right? So you want to have lots of opportunities to have success. So probably the big successes I've been involved in were for the reduced instruction set computer, redundant array of inexpensive disks or RAID. That's very widely used. And the less well-known one is the network of workstations projects, which led to kind of the cluster computing that's used by search engine companies like Inktomi and stuff like that. So we played a role there. So that's 3 projects, each 5 years over a 40-year career. I was involved in about a dozen projects. So, 9 of the 12, produced great students, lots of papers, but didn't have a giant impact. 3 of them had pretty big impact, which was pretty cool. But that's probably kind of, if whatever, 1/4 of the time the research has real impact, that'd be great. But it's important to try to have impact. If you're lucky, you'll bunt for singles or you'll play defense in soccer the whole time and you'll kick a long ball and it'll go in. If you're lucky, that'll happen. But probably you got better chances of scoring if you're trying to score, if you're trying to have impact. So that's the advice I would try, which is probably contrarian to what a lot of young people think is the safe path to tenure, which is just write as many papers as you can.
Dave, I think that your story can be sold to Hollywood.
I'll do it. Yeah. Well, I'd watch it, but I'm not sure how many other people.
If you're looking for a manager, yes, I can do that for you.
Okay. Yeah. That'd be great.
Yes, Bruno. Yes, you can.
Okay. Yeah, I think it's time to wrap up. So
I've used up the whole time allotment.
No, actually, if you have a third talk, we'd be more than happy to have it. So
I've used it up, but thanks a lot for your patience.
We're feeling a bit guilty because you had to start so early in the morning. So we're already very thrilled to have spent this moment with you. And I think I'm not just speaking on my behalf, but on behalf of the world research community in France, because we still have more than 100 people with us currently, and I think we almost reached 250 connections in the middle of your talk. So clearly, and you can also read all the thank you notes on the chat. So thanks a lot. We really appreciated the time and attention you spent.
All right. Thanks for the invitation. Bye-bye.
Thank you, everyone.
Thank you very much.
Okay.
Bye.
Bye.
Merci.
See you.